Welcome to the video key for the Unit 11 take-home test. Just for those of you who will be skipping ahead, anything you see highlighted in yellow is something that I'm going to do on the video. Anything that's highlighted on green is something I'm not going to do in the video. I'm going to expect you to do on your own. So for these first few, I've filled out a lot of them already, so you can check your work. I want to look at just 2 and 7 with you. Temperature and the solubility of a solid in a liquid have a blank relationship. So the solid in a liquid that we did in class is a sugar cube. So sugar has a higher solubility and a higher temperature. So that's a direct relationship. Okay. Hot water dissolves more sugar. So more solid dissolves at a high temperature. So that's the same direction, direct relationship. Number 7, a blank solution is when more solute can still be dissolved. So it's not full yet. It can still take some more solutes, which means it's unfull or unsaturated, right there. Unsaturated should be in your blank. And I'm not going to write it in case you have me on mute. Okay. Go ahead and push pause if you need the rest of this. Number 14, okay, label the water molecule below. I taught my students that if you're writing a H kind of hastily like that, you can see the plus sign. So the hydrogen ends are the positive ends because they're less electronegative. Oxygen is more electronegative, so it's going to hog those electrons and be partially negative. And then you need to name this shape. That's linear, bent, trigonal, planar, trigonal, pyramidal, or tetrahedral. What shape? 3 things that we can do to make a sugar cube dissolve faster in tea. These are things we did in class during that demo day. You can increase the temperature. Sugar dissolves better at high temperatures. You can stir it or agitate. Okay, if you stir the sugar, it will dissolve faster. Agitate is the fancy word for that. Or you can crush it. Sugar in a powder form will dissolve faster than a sugar cube will. This has not pressure. Okay, pressure has no effect on solids or liquids. So changing the pressure will not make sugar dissolve faster. Okay, if you want to check your answers down there, I think we're going to look at this. Compounds are chemically bonded together, C with C. Chemical compound, that's a chemical change. So chemical compounds are pure substances that cannot be separated by physical means. They have to be chemically separated. All right, let's flip over to page 2. Page 2 is where we've got our solubility curves. Now I just want to run over this with you. A lot of people have not been noticing that it says 100 grams of water here. So if you see 100 grams of water in a question, that means according to this graph. That's not something you're really looking for. All right. I've been really surprised how many people are confused about this. If they're saying least soluble, solubility is here, just like temperature is here. So this is a low temperature, and this is a high temperature. So if this is solubility, this is the low solubility, and this is the high solubility. So which substance is least soluble at 70 degrees? Okay, these guys go off the graph, but we can kind of assume they're going to continue their trends. They're going to dissolve a lot, which means dissolving the least would be right there. NaCl dissolves the least there. Right. Go ahead and check some of that. We are going to do 23, 24, and 25 together. Like I said, we've got 80 grams of KNO3, 100 grams of water, and 50 degrees Celsius. This 100 grams of water isn't something that we're going to worry about, because that just means according to this graph right here. So I'm going to take 80 grams right here. Oh, look, temperature. I almost did it. 80 grams of KNO3. That's right here. And I'm going to go to 50 degrees. And the line, the point that intercepts right there, is right on the line. So if you were on the line, that means you're full. That's the saturated part. Okay, that means saturated. If you are anywhere under the line, then you're unsaturated. Above the line, you're supersaturated. Now, what temperature do these guys have the same solubility? That says where do they have their intercept? Where do KNO3, which is this one right here, I'm going to put it in blue. Or in fact, why don't I even do this? Where do KNO3 and NaCl, which we'll do like this line right here, have the same solubility? That's where my lines cross, so it's right there. So that would be about 38 grams at about 24 degrees. Okay? It's asking me for temperature specifically. So you can say 23, 24 degrees, something like that, 24 degrees Celsius. Again, 110 grams of sodium nitrate in 100 grams of water, which we don't need, at 40 degrees Celsius. Okay? So NaNO3, I'm at 40 degrees, so I'm going to come up like this. They're saying 110 grams, so that's up here. The line represents where it's saturated. So if it's over the line, then it's supersaturated. It's dissolving more than it really should. Okay, so supersaturated for those ones. Alright, for 26, 27, 28, you need to write in full sentences. Okay, you need to write in full sentences. So I have my work here so you can kind of check it out. You need to make sure you're saying yes or no here. And you can check my definition to try and decide. It's talking about the graph up here at the top of the page. Rock candy is made by creating a supersaturated solution of sugar and water. What happens to the solute, the sugar, when you place a crystal of sugar on the string? Okay? And the solute, the sugar, is going to crystallize and form a precipitate. You can get 1 point extra credit if you go ahead and write yum with a little smiley face. I'll give you 1 point extra credit just to show that you've been listening to the video. Okay. Down here, number 28. If you leave a can of soda out on a shelf for 3 months, it's going to stay dissolved. It's going to stay carbonated. But as soon as you open the soda, it can go flat. So when you remove a cap, pressure is going down. That's what I said here. And that's when the gas can come out. So it will become less soluble. The soda is going to go flat. Carbonation can escape. So when pressure goes down, when you open the soda, the gas is not going to be dissolved anymore. The gas comes out. That's why the soda goes flat. Go ahead and flip it over, push pause, rewind if you need. Back here, write full sentences. Use words like polar, nonpolar, immiscible, I suppose would probably be too much for y'all, but you could say insoluble or whatever, something like that. Okay, I want you doing number 30 on your own, but take a look how I did 31 and 32 and 33. Down here, for problems 34 through 43, you have to show work. No work, no credit. So I have a lot of the answers here, so you can check your work, but if you do not show your work, then you will not get credit, even if you have the right answers. So make sure you're doing that. The first thing I always make my students do is box in your givens and circle your unknowns. So because I have moles, liters, and molarity, I'm going to come to the back of the periodic table and find that equation. Moles, liters, and molarity. So I'm going to plug in to this equation. Moles right there, liters right there. Make sure you're not plugging it in upside down. So here's your right answer. To 2 sig figs, you'd round it to here, and the unit for molarity is capital M, molar. Make sure you're showing the work. This doesn't count as the work. Show the work, plug in the numbers, and then you can solve it and check your answer if you haven't. For 35, I'll let you check your answer. 1.3. It's about the same as we did 34. So check your answer, but you should be showing your own work if you want credit. 36 we're going to do together. It says find volume, so that's liters. Volume in liters is what I'm looking for. Needed to make this concentration with this number of moles. So I always copy down my equation. Moles equals, molarity, concentration equals moles over liters. And then I can plug in what I know. I know what M is already. 0.100 M equals moles, which I know, 0.250 over liters, which I don't know. So I'm going to go ahead and put X there. Alright. Now anytime what you're looking for, your variable, if it's in a fraction like this, you need to cross multiply to find it. So we're going to cheat a little bit by putting this one over 1 as well. So now I have a fraction equals a fraction. Dividing this by 1 doesn't change it, so I'm allowed to do that. That didn't change it. And then we're going to cross multiply. So I'm going to go ahead and just kind of lasso this. This number times this number divided by this number gives me X. So if I cross multiply, really if you want that written a different way, you'd say 0.250 times 1, which is just the same, equals X times 0.100 divided by 0.100 divided by 0.100. Right. And then we'd solve for it. Okay. Excuse me, I'm having a hard time there, apparently. Okay, 0.250 divided by 0.100, 2.5. And the unit that we need, that's already to our, well, 2.5. Technically, this should be 2.50 for sig figs, because we've got 3 significant figures here. So on the test, we would have put that extra 0, even though my calculator didn't show it. And then it says volume in liters, so I know that's my units. All right, down here, I'm going to have you find the answer yourself, but I'm going to get you started on the work. All right, so this one is saying how many liters, so that's what I'm looking for. I'm looking for liters. I'm looking for X is needed to make grams, and it gives me a molarity. So I know that this is 1.5 molarity equals moles over liter, not grams over liter. So I cannot put 83.4 here. I'm only allowed to put moles, which means if you're given grams, you have to convert grams to moles. So I'm going to say 83.4 grams of sodium chloride, and I need the formula in order to do this. I need to know what the formula is. So we're going to come up here and say sodium Na and chlorine Cl. Sodium is an alkali metal, so it's in family 1, and it will lose 1 valence electron, making a +1 charge. Chlorine's a halogen in family 17, so it needs 1 more electron to be like the noble gases. And crisscross our 1s, they cancel out. So the formula is just NaCl for sodium chloride. So I'm going to say this many grams of NaCl. I'm going to just go down my units, go from the top to the bottom, grams of NaCl. And I need to turn it into something that fits in the equation, so I need to turn it into moles. Okay, a mole always gets a 1 in front of it. Grams is going to get the molar mass. So for this one, I'm going to need to take out my periodic table and say 1 sodium plus 1 chlorine and find the molar mass there. So 22.990 for sodium plus 35.453 for chlorine, 58.443. So that's the molar mass. That's what we're putting here, 58.443. This times 1 divided by the bottom, right? So 83 times 1, which doesn't change, so divided by 58.443 equals 1.427 moles. That's not my answer. That's my moles. 1.427. And now I can solve for X the same way I did my algebra up here. All right, so finish that problem on your own. Let's go ahead and turn it over. Page 4's got a little bit more math. Okay, number 38 is a lot like we did the other one. It gives you grams and liters, and you're trying to find molarity. So I'm going to have you show all this work and find it yourself, but I'm going to help you write the formula, because you cannot find moles without the formula of this, because you need the molar mass. So sodium is Na. Nitrate, this is not nitride, so it's not nitrogen. Nitrate, ATE, is on the periodic table. Nitrate is NO3 minus 1. So I'm going to go ahead and write that down as the formula. NO3 with a minus 1 charge, sodium makes the +1. So when I crisscross, the formula is NaNO3, which means when I find the molar mass, it's 3 oxygens plus 1 nitrogen plus 1 sodium. That's what I'm going to use here to convert to moles. For number 39, I gave you the answer, but you have to show me all the work. And again, you need to go grams to moles, and then plug moles over liters for concentration. This is what your answer should be, so figure out how to do that. Okay. Number 40, we're going to work together because it's looking for moles. It's the same equation, moles, liters, molarity. So molarity equals moles over liters. And this time I know what my molarity is, so I can say 2.56 equals moles. I don't know what moles is, so I'm going to put X for that, over liters, which I do know, 0.275. Alright, now again I've got my variable in the fraction, so we'll cheat by putting this one over 1, because 2.56 divided by 1, so 2.56. So it didn't change anything. We're allowed to do that. And then we can cross multiply. This one times this one divided by 1 equals X. Okay, we can go this times this equals X times 1. So I'm not going to solve it for you. I'm going to have you solve it doing that work. For number 41, I'm going to show you the work. All right, so I'm showing you the work, but you need to find the answer. On the quiz, a lot of students were missing this. They were plugging numbers in the wrong spot. So it's asking you how many milliliters. That's a volume of this concentration. So I put the V and the M there. Would you need to prepare 300 milliliters of this solution? So this is where I start, and this is where I'm going. So now this isn't this equation anymore. This is our new equation. We'll come right back here. M1, V1, M2, V2. Just like Boyle's law up here. And Boyle's law was inversely related. And down here the dilution equation is also inversely related. So a lot of my students went this first one times the second one divided by that, and that is not the answer. Okay? It is the first volume is what we're looking for. I'm looking for the first volume. So the first concentration should go right here. And then these two numbers get multiplied. I divided by 4. So this times this divided by 4. And then remember, it's an inverse relationship. So in this case, my molarity is going from 4 to 0.6. So my molarity is going down, which means my volume has to go up. So I will give you 1 point extra credit if you add that right there. And maybe go ahead and put extra credit like this and circle it nice and big so that it sticks out from your work. We remember to give you credit for that. Number 42, we're going to do the work together. All right, because I kind of skipped ahead here, but it's asking you for milliliters. Milliliters is a volume, and it says of this concentration. So that means those two numbers go together. If this is V1, then this one has to be M1. Are needed to make a new solution, so here is my new volume, V2, of this concentration. So there's my M2. So we're going to use M1, V1 equals M2, V2. And I can plug in what I know. I know M1, 2.50, and I'm going to say times X, okay, equals M2, 1.200 times 600. Okay. Now my answer is being multiplied by 2.5, so I have to do the opposite and divide by 2.5. That will make it go away. So now it will just be X on this side. And then I do the same procedure over here. 2.5. Okay. So we can go 1.200 times 600 equals, divided by 2.5 equals 288. And the unit, it says milliliters. So ml. 288 ml, milliliters. Now let's just check and make sure this is making sense to us. Okay, our concentration is coming down, just like it did here, which means my volume needs to go up. That's not a good sign. I did this wrong. 600, 1.2. Let's see if we can figure out what happened. Oh my goodness, I figured it out. I didn't do it wrong. I just thought I did. My molarity is not going down. My molarity is going up, because look, I'm going from here to here. Okay, so if you want to think of it this way, I went from 2.5 concentrated to about 1.2, which means if I am getting less concentrated, we should be having the opposite for our volume. So we've got that relationship. Here's the bigger molarity, so it should be multiplied by the smaller volume. Sorry if that confused you. It confused me for a second. All right, number 43, we're going to let you solve it because it's about that same way as 42. All right, down here, I gave you an example for each of them, 8 words or less. So I don't want you to copy word for word from your notes or from Google, but just kind of give us an idea. So I'm going to give you 1 point extra credit for each of these if you read these words. Saturated for me, I always think that saturated equals full. Okay? If I am saturated, I am full. Whether like a sponge is saturated when it's full of water, or if I ate too much food, I'm completely full. Unsaturated, I always think of as unfull. You can still eat more. Okay? You're weak Kool-Aid because you can still dissolve more sugar. You have more room. All right? For a supersaturated solution, you are super full. You ate as much as you possibly could. You got saturated, and then someone offered you chocolate cake, and you're like, well, okay. So now you're super full. If someone pokes you in the belly, you might puke. Right? If someone pokes you in the belly, the supersaturated solutions are going to spit out crystals or precipitates. They're going to form that rock candy. It'll fall back out. Okay. And then the extra, right, go ahead and check that one out, see if you can get those. So there's 3 points extra credit and the one there. Okay. Page 5 scares me. I will tell you that right now. Page 5 scares me. Absolutely, these are going to be the questions people miss most. I think most students will do better on the math than they do on this vocab. So I will give another point of extra credit. Holy cow, we're loading those up. If you draw out this Venn diagram. Okay. So the big circle represents something being able to dissolve. The smaller circle represents something being able to dissociate. So I labeled them there with the colors. So salt and sugar both dissolve. Dissolve means to break apart and disappear. So if you put salt or sugar in water, it's going to disappear and become a solution. The difference is ionic things, the salt is special. When it disappears, it changes. It forms ions. Okay, it has a charge or an ion. A cation is a positive, anion is the negative. Okay, so ionic things can dissociate, and that makes them electrolytes. Okay, Electrolytes. So here for this one it says ionic salts completely dissociate and dissolve. It does both. Okay, it doesn't evaporate, so we're going to cross that one out. Ionic things dissolve and dissociate, forming strong bonds. No, it's breaking bonds, so it's not this one. Forming strong electrolytes, dissociate electrolytes. Forming strong nonpolar substances. Nonpolar means covalence, and we just said ionic, so looks like there's our guy. For number 46, please write this out for yourself. As the temperature of water decreases, okay, so as temperature goes down, the amount of gas that can be dissolved. So whenever we're talking about gas in a liquid, I tell my students to think of soda. As temperature is colder, how much gas can be in there? Is it going to be flat or is it going to be carbonated? Okay. I taught my students that fast gases escape. If you are running fast and you are somewhere you don't want to be, you can find the exit. If you're walking slow, it takes you longer to find the exit. So as the temperature of water goes down, the amount of gas that gets stuck, it has to stay dissolved, goes up. The amount of gas in there. So cold soda will stay carbonated longer than warm soda. Because in a warm soda, hot particles move faster. The gases can find the exit. So if something is colder, there's more gas in it. It's more carbonated. More CO2 is dissolved. Which, if you wrote this out, helps you answer number 47. Temperature and the solubility of gas have what type of relationship? So the solubility of gas means the ability of gas to be dissolved, which is what we did here. When temperature goes down, it's easier for the gas to dissolve. So it's opposite directions, which means inverse. It's an inverse relationship. Okay, take a look at 48 and 49. And then for 50, pressure and solubility of gas in a liquid have what type of relationship? If you knew how to answer 49, you should know this one. If you keep a can of soda closed, if you don't open it, it will stay carbonated. It's not going to go flat until you open it. When you open it, pressure goes down, which means the gas can get out. So the gas is not dissolved anymore. It goes flat. Okay, so solubility of a liquid. When gas is less soluble, that means it's a flat drink. It's not carbonated anymore. So they're going in the same direction because that is a direct relationship. So pressure in gases are direct, temperature in gases are inverse. And careful. Alright, here we're going to go ahead and have you reference this right there. Okay. We said electrolytes mean dissociate, mean ionic. So you need a metal and a nonmetal, like NaCl. Metal, nonmetal, that's ionic. Ionic salts, yes. PO4, those are both nonmetals, so that is not an electrolyte. Calcium and nitrogen, metal, nonmetal, ionic. H2O, both nonmetals, does not conduct electricity. Covalence, nonmetals do not conduct electricity. So those are the three that will dissociate and dissolve, will form electrolytes. That means they can conduct electricity. All right, we're going all the way down there. Check your work. 56, I think without contest, 56 last year was the most missed test question, the question like this. All right, so for this one, man, you know Charles watches DirecTV. Almost everyone knows that this equation is direct. Gay-Lussac looks just like it, so it's direct. Boyle's pressure and volume was an inverse relationship. Boyle's looks just like our dilution equation. So when something is more concentrated, it'll have a smaller volume. So what they're saying here is if we have this volume of a solution and this concentration, what happens if I evaporate off half the solution? All right. So if I make this down, if I take my volume and my molarity, if I divide my molarity by 2, I evaporate half of it off. So instead of having a liter of Kool-Aid, I have half a liter of Kool-Aid. Then that means this one gets multiplied by 2 because it's an inverse relationship. Okay, because the Kool-Aid doesn't evaporate. The water can, which means we're going to be twice as concentrated. Okay, so it would go up to a concentration of even 4. Okay, if volume comes down to 1.5, concentration goes up to 4. See if you can do this one. Okay, you have 3 liters and you double the volume. So you have Kool-Aid and you add twice as much, 3 times as much water as you should. Is it going to taste better or worse? Okay, is it more concentrated or less? Okay, page 6. All right, so on page 6, this first column you need to decide if it's soluble or not using the chart up here, and then you need to write the name. So PB and I2, I'm going to find PB over here. PB is right there. It's lead, and it is a transition metal that needs a Roman numeral. Okay, lead will need a Roman numeral because it's not in the exception block and it's not in the first 2 families. So I'm going to call this one lead blank, and I is iodine, which I will change to iodide. Okay, to know what charge it's making, we can uncriss-cross, but really there's an easier way. It says right here, lead 2. So that's lead making a 2 charge, so I'd call it lead 2 iodide. And then we're going to check it out. So lead is here, iodide is here. That's I, insoluble, which means it will not dissolve in water. Ta-da! Over on this side, same idea, but now you're writing formulas. Okay, so do the first 2 on your own. Copper 2 acetate. Copper is Cu. Acetate, ATE, means I'm going to find it on my polyatomic list. It's the first one. Parentheses C2H3O2, making a -1 charge. Copper, it tells me right there, is 2. Copper making a 2 charge. So I can crisscross the 1 in front of the parentheses and the 2 behind it. Cu, invisible 1. C2H3O2, 2. Like that is my formula. And then we come up here. Copper acetate is S, soluble, which means it's able to dissolve in water. All right. Great job, y'all.